Okay, let me hit the share screen here and let me see if I can get everything up. And, okay, can you guys see this?
Yes.
Yeah, I got it.
Everybody got it?
Indeed.
Okay, all right. So I'm going to go ahead and start talking. So everybody, definitely chime in when you can. No one doesn't work to raise your hand, I guess, in this kind of format. The one request, my understanding, is that sometimes people put their microphones on mute initially until they want to ask a question or make a comment or something. I'm going to go through probably 10 slides or so, and then I'll have like a kind of question-answer slide, and I can do some drawings or whatever that's needed. Did everyone get those files that I sent out? Of course, I just asked you to
Yes, sir.
Okay, I just asked you to mute your microphones. Okay, sorry. Okay, anyway, so I might refer to a few things here or there. Those are mostly for reference, but those slides are basically, when teaching digital electronics, I like to provide students with a lot of additional information that's not in books, lots of examples, lots of solved problems, sometimes alternate methods for doing things. And so I've written up some tutorials. There's a couple of them I put there. For combinational logic tutorials, I have some sequential logic tutorials I'll put up later. There's anything that the students can use that may help them, because it's a difficult topic, and students, seeing things different ways usually helps out. Let me just move forward here. Okay, so the focus of this is I'm going to give the instructors of digital electronics here a little bit insight into the topics that the students typically have trouble with. This is obviously, it's not a full lecture of digital electronics. I'm basically going through a full course of material, basically going item by item and kind of identifying what the students typically have problems with. Some of the solutions and some things I found that really help out. And I've been teaching this course first at a higher university and then here at Cincinnati State since 2005. So I've probably taught this class 15 times now. And there are definitely some common themes that run through that students ultimately have difficulty with. I want to provide a number of examples and techniques that students have found helpful, which are not found in textbooks. And I put, but should be. There's some shortcuts and things. But textbooks, and rightly so, are very pedantic in the way they do things. And sometimes students like to see things done differently. And finally provide a little more detail on all the topics that are on the CTAG outcome rubrics, just in more detail. Okay. So for this course, basically, Lecture 1, I'm really just going to be focusing on kind of the real intro core aspects, binary numbers and other formats, differences between binary numbers and digital codes, negative numbers, binary addition, truth tables, logic gates, and then some simple circuits. So I don't know if we'll get to all this today, but that's the idea, and what we don't just carry on until tomorrow. Students have difficulties in every aspect of this, of course. Sometimes it's very surprising that what they find they have difficulty with, and sometimes there are certain concepts that they grasp very, very easily. I usually start out, for many people, I don't have to justify why digital electronics, but the students who are taking it for an EET type degree sometimes do want to know. Basically, the study and analysis of discrete signals, usually having two values. And this is, of course, I always give the example of your sensor that's in your car, that you put your key in the ignition and you open your door, and what happens? The buzzer goes off. Well, there's two conditions. You've opened the door and you have the ignition. If you take that out, then it doesn't go off. And so I tell them these kinds of systems are just everywhere, not only in computer systems, but in manufacturing, whatever. The courses always break themselves down into two categories: combinational logic, sequential logic. Students typically have an easier time with combinational logic, which is how signals are combined to form an outcome. They usually get a hold of that, and then unless it's an odd layout of courses, it takes a left turn to sequential logic, and you bring in clocking and flip-flops and things like this, and that can be a fairly rude awakening to a lot of students. So a couple of things that I wanted to put down here from my experience for teaching the courses. One, there definitely is a direct correlation between the level of the math maturity of the success of the students in digital electronics, which I found to be actually quite surprising because, at its heart, digital electronics is ones and zeros, and maybe some addition. But I found that students who have higher math aptitude have the ability to think a little more abstractly. And that is greatly beneficial to being successful in this course. It doesn't actually require any trigonometry or calculus or geometry or anything, but it does require the ability to think abstractly. Solid algebra skills is also good, where you get to doing Boolean algebra. We'll talk about. That's number 2, basically. I put concurrent taking of calculus is strongly advised. That may be a little strong, but definitely pre-calc. At both OU and here at Cincy State, I've raised the math requirements for this course of incoming students taking it, and I have found better success with that. You can only do that. You're limited in how much you can do that, but I found that to be true. Students do have a difficult time grasping the concept of binary numbers. It's kind of surprising, but they really have a hard time with that. I'll talk about that in the first couple of slides. For Boolean reduction and Boolean algebra is a very difficult part of this course. Many people feel it should probably not be included, and I've been on the fence about that many times. I think that it does provide, I think that you need to understand exactly how these signals interact. Doing Boolean reduction is difficult, but I think that it really gives them a sense of what it feels like in a circuit standpoint to make something simpler, because actually they go in the lab, they have to wire it up. Say, okay, here's this large circuit, wire this up. Then you Boolean reduce and you find out it's just a couple of gates. Okay, well, that's pretty motivating. Less wiring to do. And then 5, like I said before, when the course does switch from combinational to sequential logic, it takes a big turn. It can leave some students behind. They're not really prepared for that. And then you kind of have to transition to that in a certain way, but it's fairly abrupt. Okay, so first thing I want to talk about here is binary numbers. And of course, for people who are familiar with this or have taught this course, they probably had to deal with this as well. And one of the things with the students is I try to tell them, basically what is a bit, because when they see a bunch of ones and zeros in their minds, and they see this on the computer system or in media or whatever, they don't know what a 1 and a 0 actually means. And even when they get into the lab, sometimes they start wiring things up and they don't really process exactly what's going on. So a bit is a voltage level. I tell them basically 1, there is a standard that says that it's between about 3.5 and 5 volts. 0 is a voltage between 0 and 0.8 volts. And that's what we mean by ones and zeros. That's what the computer is going to interpret. If it's between 0.8 and 3.5, it doesn't actually know what to do, and it will assign something randomly. It's not very desirable. Also, since there's a lot of functions written, a lot of you write out Boolean expressions, students see it as a bunch of math, and I try to tell them you need to step back because it's not just a bunch of math. Every one of those ABCs refers to a wire, and that's an actual wire that you have coming from it. It's an input. Every output goes to a lamp or goes to another part of a circuit or something else. So if you have A, B, C, D, this is 4 signals coming in where each signal can be 1 or 0. Therefore, A, B, C, D can be a host of inputs, and we'll talk about that later. So basically, one of the things I really try to do in teaching these courses is to tell the students what all this means. I don't really want them to get lost in the math. That's one thing that can happen. I want them to step back and see this expression actually is wires and gates and outputs. I want them to see that and understand what that means. And then when they do something like Boolean reduction, then by reducing that, you're reducing the number of gates and wires and everything that you need to connect the kind of physical feel I want them to pull from this. This is an important diagram here. And this is basically the whole deal that at least from a high level, what I want students to understand is that we have inputs on one side, And then inside this box, you've got some kind of digital circuit, whatever it is. This is your design. You've specified some problem, and that kind of circuit is what gets the inputs to the outputs. And then for every input, you could have multiple outputs coming out. Each one can be a function, like F can be a function of A, B, C, and D. G and H are both functions of those inputs. So you're not restricted necessarily to just one input, a couple of inputs and one output. Most circuits are taught that way initially, but that's not always the case. So this is the kind of thing that I want them to understand, that that actually this is the deal. We have these binary signals coming in, and the outputs themselves are binary signals because that's all we're dealing with in digital electronics. F is a function of these inputs, but F only has the value of 0, 1. And so that's something that I try to really drive home because I'll talk about the flow of this digital electronics, which is that you're given some sort of design. You're given some sort of a problem like the car sensor or something like that, or one they build in our labs, which is an alarm system for your house. It's okay, well, you've got a window sensor, you've got a door sensor, and if it goes off, then there's an alarm, or maybe there's a light or something like this. And so you have your input. The sensors are on one side. You have to build the circuit, and your outputs are this, maybe a light, and then maybe an alarm. You have two different outputs. And so I want them to kind of get this overview, and I think that's very important. I actually showed this in the class a few times.
Hey, Ralph, I don't know if it's just my connection or not, but you drop off a little bit, and it's kind of quiet. I don't know if there's a way, unless others maybe aren't experiencing the same thing. This could be just me.
It could be me turning my head.
I'm seeing the same. I'm hearing the same thing, Rob. So yeah,
okay,
I figured I got a little background noise here, so I thought it was just me, but
okay,
now that you mention it,
it's very quiet where I am. How is this?
Yeah, when you stay close like that, it sounds good.
Okay,
yeah.
I'll try to stay out like this. It has. I'm using like a headphone microphone thing, so I'm trying to get the right positioning for it to sound fine.
Great.
Yeah, much better.
Okay, that's good. All right, let me see if I can turn it over even a little bit more. That's fine. Okay, but yeah, definitely let me know if you can't hear it. So anyway, let me just move on. So one of the things about it is that I try to tell the students is the concept of a number system. Because once you write out a binary string, a lot of times they just don't understand what that means. And you always have to relate it to something they know, of course, which is the decimal system. So, I like to write things out like for any base n system, the numbers are constructed, as this. All the weights are of 0 to n minus 1, and then it goes n 0 all the way up. So this exact same thing that you have in decimal systems. 985 is 9 times 100 plus 8 times 10 plus 5 times 1. And I tell them, this is what you learn in first or second grade or third grade, whenever it is you learn this. And they don't. It kind of is difficult for them to look at the initial expression there, where you have the initial expression up there, where that doesn't make a lot of sense to them. It's very kind of algebraic. But once you kind of put it in place, you say, okay, well, base 2 can only have zeros and ones, in this system. So it starts at 2 to the 0, 1, 2. Also have to drive home that it does begin at 2 to the 0. That's something that I think everyone who teaches digital electronics has to battle it. You start counting at 0 instead of 1. So that is always an issue. So, but the idea here is, I tell them, you could use any base you want. This could be base 5, base 7, whatever. But as is kind of a general theme in this course, everything is done on powers of 2. So base 2 and then base 8, base 16, which we'll talk about in a little bit. So this is what it all means. So I try to tell them that for any binary number, so if you have this near number here, 101101, then basically you're counting the number of places you've got 0, 1, 2, 3, 4, 5. That's right. And then basically they're just weighted by the powers of 2, and you just add them all up. And this seems to make sense, but of course one of the main problems that I have with this is they'll start counting the so-called least significant bit, which is this one here, and then the most significant bit, which is this one here. They'll start counting the least significant bit as 2 to the first, and then everything gets messed up. So, you know, many examples need to be run, and there's a lot of homework, and a lot of quizzes and things like this to ensure they understand their binary numbers. There is a one thing that happens is most students have calculators that will do binary numbers. A lot of them do. So they just kind of have to watch for that. And when they do homework, a lot of times they'll just write down the answer, and be very careful to say, you know, you really need to show your work, and they have to kind of spread this out so they really understand it. I say here that I'm not a proponent of memorizing material, and that's true. I think many things for this course you don't need to memorize, but I do think there are a few things that you have to commit to memory. And I do want them to know all their binary numbers from 0 through 15. I tell them that, you know, if I were to wake them up at 2 o'clock in the morning and yell, you know, what's 9 in binary, I want to hear them say 1001, and that's it. You know, it's kind of like a boot camp or something. And because there's so many things that you see in the lab and building truth tables and everything that is really, what am I say there? It's definitely less taxing if they have that stuff to memory. Also, knowing the powers of 2 up to 2 to the 10th. This is helpful for being able to convert things to binary numbers without having to constantly write down powers of 2 tables and work it all out. And there's mnemonics. 2 to the 10th is like 1024. So, and there's 2 to the 6th is 64. I mean, there's a couple of mnemonics people can use. And I'm sure there's ways to do that. There are a lot of online resources. There's various binary quizzes and games that people can play. There's one that's like a Tetris kind of thing. You know, binary numbers come down. You have to write down what it is before they all pile up. Something like that. So I do encourage them. I have a couple of links. Maybe I can put those in a document, send them out. There's a couple of links. Cisco, actually, the Communications Corporation, they had a pretty cool little binary game where students. I encourage the students to do it. I don't think I've ever really assigned it as a problem, or an assignment, but I do encourage them to do that. Converting base 10 to binary is, of course, very important. There's 2 methods. The one that books promote a lot is this divide by 2 method. So if you convert this number 254, you just start divide by 2, and you keep doing this, and the remainders are going to be your binary number. So you just divide by 2 and keep going until you hit 0 with a remainder of 1 or whatever. The problem here is that the binary equivalent is the number flipped upside down. Okay, so the last thing is your most significant bit. At least significant bit is written this way. Students very frequently mess this up for 2 different reasons. One, constant division means they'll make a math error, you know, especially when it's a fairly large number. And then 2, they'll write the number wrong. So instead of here being all these 1s and a 0, they'll put a 0 and then all the 1s. And then, of course, you've got a much smaller number. So I usually don't recommend. I will get some assignments because students, sometimes they'll do this. It's you know, students like algorithms. They like knowing a method for doing something, you know, versus having to really think about it. That doesn't sound good, but having to really think very deeply about it. This is kind of just a rote way of kind of doing it, as long as the math works out. But I have to say that I see students mess this up probably 30% of the time doing it this way. The other method that I really try to encourage them to do is really just to know the powers of 2 and just subtract the numbers and just keep going. So if you got 117, the nearest power of 2 is 64. That's low enough. You know, of course, there's 128 right above it, but 64. So 64 is 2 to the 6th. That means we need 6 bits for 2 to the 0 through 2 to the 6th. So I say, okay, so lay out 7 bits, you know, 7 dashes, you know, put a bunch of bits out there, and then start subtracting. You know, so we got 53, and then you go to 32 and 16, 4, etc., and then you write the number out, and there you have it. I think this is a much better way of doing things for the students because when they get good at it, it's quicker. There's a little bit less algebra, and then when they get down anything that's below 16, they just write the number out because I tried to tell them to memorize 0 through 15. So when it gets down to you know, something like 5, then they just, you know, write down 0, 1, 0, 1, and they're done, and it just goes very fast. And so So this can be done fairly quickly, and that's my recommendation. They do have more success with this as long as, like I say down here, as long as they don't forget their powers of 2. So I do recommend this as the way to do it. And of course, I give them homework on doing both of these. All right. To really help students understand binary numbers, they really have to work a lot of problems. This is one of the things about the digital electronics class, is that really students have to put in a lot of time and work a lot of problems. I try to tell them this that this is even more so than the homework problems. There's other problems in the book. There's usually the odd answers are in the back of the book, or if they want to come to me and work some extra ones. And I try to make it as interactive as possible. I get the students up on the whiteboards, working problems, usually in pairs or threes. So I try to get them doing as much as possible. Homework, obviously, online or in-class quizzes. Constantly quiz the students when you're covering a new topic. So if I'm doing a new topic, I'll say, okay, and this is 14. So what's 14, everybody? And someone will say 1, 1, 1, 0. Okay, fine, that's good. And then I do provide links to the binary quiz games, but like I said, I usually don't enforce that, but I'm beginning to think I might. So questions and comments about this part so far? Anybody have any questions about this?
I know when I do that, convert from like a base 10 to a base 2, I do a similar thing as you. I have them like write out just a byte on the 8 bits, and right. I tell them to put, accept the bit with a 1 if putting it there does not exceed the value of the number you're wanting. So if it's 117, they have 128. I'd say, okay, so you'd put a 0 on the 128 because that would exceed it. Then you go to 64. If putting a 1 there exceeds it, no, it doesn't. So put a 1 for 64. Then what about adding 32 to 64? Yeah, put a 1 there. And the same way as what you just described with the difference thing there. And they do like that better than the divide by 2. I agree with you 100%.
Yeah, I think so. I didn't talk about the fact that sometimes their answer has to be a specified number of bits. That also happens. So say, okay, you have an 8-bit word and you have to write some number, then yeah, you do have to look at the higher ones and say, okay, those are zeros, those are zeros, those are zeros, and finally get down to whatever. Right. Yeah. Yeah. So that happens also, and especially once you get a little bit later in the course and start talking about some other things. But yeah, but it is interesting that I find students, and it happens every semester, and it stuns me every time, which is I'll have a question on the final exam. Write 78, base 10 in a binary, and, there'll be, 5 students out of 25, they'll get it wrong.
Wow.
And it just, yeah. And I'm like, really? You just went through an entire semester, but it's one of those things that some students, and I've had students come to me studying for the final exam. I just don't understand how to do binary numbers. So it is something. It is something that it seems intuitive when you've done it for a long time. But the students do actually need a lot of reinforcement on that. So I think as much as you can put into that early on is worthwhile.
It's interesting. I had an industry guy explain binary to me. I don't know, a while ago, and what he did is he wrote out the binary sequence of numbers, right, 1s and 0s, right. And then he went from the rightmost number and he put a 1 and then started working the pattern back, 2, 4, 8, 16. He said, if there's a 1, you add the number. If there's not a 1, you don't.
Right.
And I'll tell you, I had almost 100% success rate explaining that to my seniors last year.
It works.
So
it worked. That's right.
At least that group of students got it based on that system. So I don't know.
I think for when you're looking at a binary number and you when you're doing what you said, which is basically just starting there and you're just adding up all the ones that are ones. Mm-hmm. That does work well when you're trying to convert like a binary to decimal. The other way around, it's a little trickier.
It's a little trickier, sure.
Yeah, they have to ferret it out a little bit. But most of them, and this is where the math ability kind of comes in. They can kind of reverse that process and pull it back out. And that works fine. I still have students that will do the divide by 2 method simply because that's a process and it seems comfortable to them.
Mm-hmm.
Yeah. So, but it's one of these things that you want to present it in as many ways as possible because it's just for some students something clicks and for other ones other things click. So you just have to kind of go about it because sitting there at a board saying, well, it's like this, and they're like, I don't understand. You're like, well, it's like this, and they're like, I don't understand. I mean, that'll drive you nuts. Okay, so let's move on.
Thanks.
Okay, so other number formats, depending on what people do. Typically, it will cover octal and base and octal and hex, base 8. Again, this goes to the same thing I tell the students. It's just another number system. It's just base 8 at 0 through 7. And once they've kind of got the concept, and I'd say it's almost exactly the same as decimal, except we just stop at 7. We just don't stop at 9. And when I have students say, well, what about writing 10 on base 8? And I'm like, well, it's an 8 and a 2, so it looks like 1, 2. They're like, oh, okay, now I get it. So you just have to give a lot of examples, and like this one, 142 base 8, and you just put in the weights, and you tell them it's the way that you just add these things up. So this isn't not too bad. Of course, now going the opposite way between binary and octal is fantastic because octal just have 3 binary bits. You just take the number and you just write down the binary bits, and that's it. 142 is 001, and 4 100, and the 2 010, and you just put them all together, and there's your binary number. Students are usually amazed. They think this is some sort of sorcery that this actually works. But I'm saying the reason it works is because this is 8 is a power of 2. You can't do this if it's a 9 or an 11 or something. It doesn't work out. I do tell them you do have to start with the least significant bit because if you might have to add some at the far end. And then the binary to octal, the same thing. You just go and you split them out into every 3 bits, and then you just write down the digits that you have. Obviously, no digit can be greater than 7 because we're talking about octal here. And this works pretty well. I don't have a lot of problems. Some students mess up. They don't start at least significant bit if you're going binary to octal, and they'll start at one side and run out of bits and kind of figure out what to do. And this is another reason I tell them you really need to know your powers of. You need to know your binary numbers, so that when you see 101, you think 5. You see 001, it's 1. So that this actually works pretty well. I don't have too many problems with this. Same thing for hex. Hex, of course, is I do try to give them a couple of examples with programming. I talked to them about how in like a second digital electronics course, we would move on to looking at various microprocessors and look at assembly language. And I tell them a little bit about what assembly language is, machine code, and programming and things of this. And I say, you do a lot of your assembly language programming is done in hexadecimal. All the values you choose, the values that you choose for the registers, the addresses, whatever you're using, is done in hexadecimal. I said that's further converted down back into binary once it goes to machine code, but that's the idea. And I said, so hex, again, here we're looking at another power of 2, being 2 to the 4th. We have 0 through 9, but we have to represent 10 through 15. They've done A through F. And I had the student comment the other day. I wrote a number out, and he says, hey, it looks like a Canadian license plate. I was like, yeah, actually, that's true. I hadn't thought about that before. It does. So now you're bringing this in, and this works pretty well. I mean, you can get some very large numbers in hex very quickly. And again, here, you have to really know the powers 0 through 15. This is one of them, because if you're looking at something like 1010, that's a 10, or it's an A in hex, and you have to know and be able to kind of seamlessly and quickly work through those. Again, power 10s is just adding up weights. It's not a problem. I mean, your power of doing 16 to decimal, but then going between binary and hex, because it's 4 bits, it's the same thing that you do in octal, and just write them out, all the 4 bits. And here, of course, you have to keep in mind that you have to use 4 bits. Like students will take 4 and they'll just write 100. I'm like, no. You You have to use 4 bits. It has to be done. You don't have the right size word. So for A8, 1010 for the 4, 1010 for the A, and 1000 for the 8, and put them all together. There you go. And students who have a hard time believing this, I'll go through and have them add up the binary number and show them it's exact same, just so they get that. And likewise for splitting it out, binary to hex works out very well. And I do talk about that. I did actually look up the other day if octal was even still used, by the way, because I'm trying to figure out if that's it. And it is. It turns out it is still used. There's some niche applications. One of them involves Unix, actually, that's done in octal still. And a number of programming languages, advanced programming languages, which have certain key instructions are done in octal instead of hex. So it is actually still used, though it is quite a niche thing. Now, one that gives students a lot of problems is binary coded decimal. And I try to convince them what the difference is between a number format and a code. Okay, I don't go into a lot of codes. There's a number of codes that you can go into: gray code, XS3 code. There's a host of different codes that you can use in binary systems. And I will talk to them briefly, gray code especially, because it has certain applications and loaders. But binary coded decimal is one that's very commonly used anytime you need to convert between binary and decimal. And I tell them that this is not a binary number. It's really a binary code. And it's kind of like if you wanted to write a binary number and you knew nothing about binary to some extent. You only knew 0 through 9, and you just did kind of a brain dead method of doing it. This is what you would dream up. And show them that basically all you do is you're just taking the decimal numbers and writing them down with binary equivalents. 754, 0111, 0101, 0100. That's 7, 5, and 4. That is, I tell them, I try to emphasize, this is not a binary number. If you actually take that number, it's going to be huge. If you were to actually weight out the weighting of all those binary bits, it's a massive number. And they have a hard time kind of doing that exactly. And they want a good application of this, which is in the 7-segment display that you have in your clock radio. Matter of fact, each one of those segments is a different function for the inputs that it has. So there's a chip, which is a binary to 7-segment display driver. And I tell them this is one of the things we have. I give them a homework assignment. I tell them they actually have to design the logic for the 7-segment display when we do K-maps. It's a good assignment. It's kind of a long assignment, but it's a good one. So basically, I do want to tell them that this is not a number format because this binary string is not weighted. I mean, none of those things have weights. It's just a 7, a 5, and a 4. And also that you can't get a BCD digit greater than 9, because if you think about, I tell them, like, you think about a 7-segment display, it can go 1 through 9, but on one digit you can't display a 10, you can't display a 12. You have to go to another digit. So that's why. And so likewise, going back and forth here for this one, which is 8693, it really is just writing out the digits. So this gets me when I start introducing kind of the concept of codes. And this is an important aspect of digital electronics. I tell them that not everything is a number. Obviously, sometimes your computer deals with numbers in the ALU, the arithmetic logic unit. But there's an awful lot of digital signals running around that have to do with where data is to be routed and all kinds of decision making. And it's not really a number; they're codes. Sometimes it's error checking bits and all this kind of stuff. So I tell them that there really is a lot of stuff going on besides just binary numbers. That being the case, is this little problem I've given. I've given this on exam a couple times, and this always throws them because it's actually, to be fair, it's a terrible thing to put on exam because they have to move very quickly, and this is a lot to read and figure out what's going on. But the idea of this is for them to get an idea about what codes actually are inside of a computer, which I think is important. So here you have a mouse, and this is basically a chessboard. For those who play chess, it's A through H, 1 through 8. Okay, so you got this mouse which is sitting there at B1, and it's trying to get to the trophy, which is up there at G8, and you've got these cats sitting around. And I tell them, okay, so what you're going to do is you're going to be sending a string of information to this mouse. And you're going to tell him it's a 5-bit string. with the following instructions. The most significant of the two most significant bits are 0, 0, the guy goes straight, 0, 1, he goes backwards, 1, 0 turns left, and 1, 1 turns right. The three least significant bits give the distance that he's going to travel. Okay, so 1, 1, 0, 1, 1 means turn right and move 3 spaces. Okay, and the mouse turns right like I say it's like a car, so it's facing the way that it's going with its backing up. So I give him a series of codes. And I was like, okay, after these series of codes, where's the mouse? Is it safe? Okay, did it hit one of these cats, for instance? And then I say, just trying to get them to go through the sequence and, read the code and really kind of understand what the code means and get the idea that, okay, these first 2 bits mean something, these 3 bits mean something else. So the first 2 bit is kind of a direction, it tells them where data might go, and the 3 bits is the last 3 bits being what the data actually is. And then I tell them, give me a series of codes to get the mouse to the trophy. Now, most of the students will choose this path right here, which makes sense. But I don't know what gets into some students. I've had this, that. I had one student that I don't know. It was this kind of a thing. I don't know. Anyway, but whatever it is, I have them choose that and write that down. And it works. It's a nice little problem. I think it maybe is too much for a test, and I've done it a couple times, but maybe a homework problem. I haven't used it in a couple of years, but it did help students understand what the difference was between a number system and a code. I thought it was pretty handy in that regard.
Right. I saw that in your notes, and I really like that. I don't know. You just think about like bit mapping and PLCs. The stuff you're doing there where you take the first 2 bits, meaning one piece of information, the next 3 is another piece of information. I just think there's a lot to be learned from this, and what a creative assignment. I just like this thing.
Yeah, I actually, the way this assignment started out with something, I used to be an avid chess player a long time ago, and I started out with doing I don't know if you guys ever heard of what's known as the Knights Tour.
Yeah, okay.
Yeah, the Knight's Tour is basically kind of figuring out if you move it like a knight, there's a certain sequence where you can hit every square on the chessboard only once.
Huh.
It's a big mathematical puzzle, and some people claim to be able to do it intuitively, but it's the patterns. I don't know if that's true, maybe, but so I started kind of doing something like that, and it got to be hours of frustration trying to come up with a problem that made any sense whatsoever. Yeah. And so finally I was like, okay, well, I got a mouse or whatever. I came up with this. But it is true, actually, once you start looking at, students who do go on, they take like PLCs, motors, and controls, they're looking at ladder logic, things like this. It really works out well. It's a nice problem, and it is something that when they go on to looking at microprocessors, if they have stop bits or parity bits or whatever it is, it kind of gives them a sense that this is that there's more to it. And I like it. And the students have a fun time with it. Now, I tell you what happens here for some reason is the most common mistake the students make with this is the mouse goes off the board. And I don't know why that is, but they'll turn left instead of going right, and the next thing you know, things way off somewhere. That's the most common thing that happens that goes wrong here. But anyway, I think it's a pretty good assignment, and there's probably many different things that you can do similar to this. This is just one example, and this is in the packet that's mailed out. It got sent out to everybody, and it's just kind of I thought this was a good assignment, and students generally have, they kind of enjoy doing it. It's kind of, it's kind of a game. Yeah, it's just kind of a game.
It's pretty neat.
Yeah, it's not bad. It's not too bad. All right, negative number formats is one thing that students frequently have difficulty with. The main thing is I tell them that, okay, I say, you have to understand that when you're doing something mathematical in binary, you only have binary numbers. You can't stick a negative sign in front of it. That doesn't exist. A negative sign actually is an ASCII code that comes from your keyboard. It's a digital stream. Actually, so you can't do that. So there has to be a way to represent negative numbers efficiently in binary. And so I basically tell them that it's done 3 different ways. And this is, of course, in the books and everything. But one thing is that they need to understand is that regardless of what the convention is, that all the positive numbers are the same, okay? And their most significant bit is always a 0 if it's a positive number. So I say when you see that, I say, okay, keep in mind what's going on in a computer. Some things are mathematical operations, but some are not. Some, like we just said in the previous example, some things are, routing or whatever else. So when they start doing mathematical operations, the computers know that they're going to be doing signed math, okay? So once they're doing signed math, then they adopt the convention that if there's a 0 in the most significant bit, it's a positive number. If there's a 1, it's going to be a negative. And that's the way it is for every system that they use. Now, I go through I talk about sign magnitude, the various techniques. One, you just put a 1 most significant bit, and you just write the number directly. I said that this is kind of the very most simplest way that you would do this. I say there's a problem that you can only write to -7 with 4 bits, and you end up with 2 numbers you end up with a positive and -0. Okay, so no computer system likes a positive and -0. That's just not going to happen. Plus, from an engineering design standpoint, that's wasteful. Okay, so you should be able to fix that somehow. I talk about 1's complement, which is where they just invert every bit. Okay, and I say this is also another technique that you can use. The problem, again, it's almost the exact same reason as before. You can only write to -7 with 4 bits, and again, you have 2 numbers for 0. Same thing. So then I say, okay, almost 99.9% of everything is done with 2's complement, which is more complicated, but it solves this problem. And I say that there's 2 techniques for doing it, which is usually specified in the book. You do the 1's complement plus 1, or you do the so-called search for the 1 technique, which is where you start at the least significant bit, copy down the number until you hit the first 1, copy that one down, and then invert every other bit. They get the example here for like -18. If you have +18, and where I say note that the most significant bit must be 0 if the number is positive. And if you do the first one, you do the first technique, which is the 1's complement. You flip all the bits over, and then you add 1, and then that's it. I haven't talked about addition yet. Students have an issue. I usually cover addition before this. That's it. The search for the 1 is very straightforward. You start with the least significant bit. You go 0 and 1. You type those down, and then everything above it you flip, and then there you are. This is one thing that the students like. Okay, this search for the 1 technique is very quick. You can have a 13-digit word, and you just write it right out. It works very well, and it's very quick. I also like to tell them that, and to give them a little bit of a physical feel, is this is how barcodes work. Okay, so that if you actually look at the barcode in anything that you have, if you look at a barcode, it doesn't look symmetric. I say, but the actual number on a barcode only goes halfway. The other half of it is the 2's complement of that number. That's why it looks a little strange. And so what you have is, regardless of which way you scan on a barcode, you get the number and its 2's complement. So that's why you can scan in any direction. You get and then the computer's expecting the number and its 2's complement to go either way. And so that's how it was developed. And students are usually pretty interested with that. It's a good kind of real-life application for this. That works quite well. Basically, arithmetic, signed arithmetic. I have to admit, students generally don't have a problem doing adding in binary. I don't find that, I don't usually see an issue with that. Usually it works out pretty well. Just straight addition. They get the idea. You just carry numbers just like you do in regular addition. They realize that if you add a 1, 1, and 1, you get a 3. So you put a 1 down and a 1 comes up. The concept of a carry doesn't bother them. So this actually, I would say, is a topic I rarely see any students having a problem with, which is adding numbers. That works pretty well. I will say one thing in the classes that I teach, I usually don't teach fractions, and I don't do binary fractions. I usually don't teach multiplication. I do tell them that when we talk about shift registers later on, that if you take the binary numbers and you just start shifting to the left, you're multiplying by 2, and if you start shifting to the right, you're dividing by 2. Same thing happens in base 10. Sometimes if you got the number which is 150, you shift it to the left, you got 1500, you just multiply by 10, you shift it to the right, you've got 15 divided by 10. So I said, so basically, if you want to know how to do binary, if you want to do something like binary decimals, just keep shifting them to the right, and you're just going to get consistently get things divided by 2 in decimals. But that's all I'd say about it. So I know that books make a big deal, and they do a lot of math and science problems, but I don't spend any time on it. Subtraction is, as I tell them, okay, well, we have negative numbers, and we have addition, therefore you have subtraction. I mean, that's all you're doing. You just add a negative number. So if you want to do 28 minus 14, what you're really doing is you're adding negative 14. Okay, so your computer, this is what your computer does. So the computer says, okay, I need negative 14, so, oh, what's I drop one? Oh, okay, there we go. Sorry, I'll come back to that after a minute. Here it is. So first thing you do when you're 28 minus 14 is you have to represent the number negative 14. So we're going to do that 2's complement, so they can do the search for the 1, and they can flip all the bits and get 1, 0, 0, 1, 0. Again, specify that, yes, you can write. I have to keep emphasizing them over and over that when you're doing positive 14, you have to make sure that you have enough bits that the most significant bit is a 0. So in this case, you have to use 5 bits. And so then they do it this way. So then always as a check, the students always make sure they have a 1 in the most significant bit after they convert to negative. Then basically,
Gentlemen, I'm going to need to get going. I thank you very much, Ralph.
Yep. I'll see you on Thursday.
I appreciate this. Like I said, sorry I got to leave.
No problem.
Take care, guys.
All right. See you later. All right. So
Mark,
then, what's that?
I was just saying goodbye to Mark.
Oh, yeah.
I had him on mute here.
No problem. So then basically once you have that, then you got the number, you add the numbers together, and then basically you've got a couple of different conditions. Here if you have a 5-bit number and another 5-bit number, you've got 5 bits. In this case, I've got 6. I guess I specified them as 6. Okay, there's 28, and this is specified. Okay, so I had to go back and re-specify 14 with 6 bits. Okay, okay, so that's the way that works. Then you add them together. If I have more than 6 bits, I throw out the 1, and there's the answer. And I have students do this and go back and check, just to make sure this is correct. I also do point out a couple of things, that if the answer is negative, it's not going to look like what you expect. This kind of, students get a little surprised. If you do 18 minus 22, and you go through, you convert 22 to negative, you're going to end up with a negative number. Well, that number is in 2's complement. It's a 2's complement number. So to figure out what that number is, you're going to have to convert it back. So what you do here, you get a 4. So that says that the number is negative 4. And so tell students, this is, because otherwise they're going to say, oh, this is, sometimes they'll add up all those weights, and they come up with some crazy number, and I'll be really 18 minus 22 ended up being 144 or something like that. So I think, no, you just got to redo this. And then you can get bit overflow, two large negative numbers, like negative 12 minus 8, and you're going to get bit overflow because it's going to be a large negative number and it's larger than the bits you've specified. And I tell them this is a problem. Students will, this is a problem in computers. You have to be sure that you have bit overflow is an error that's given in computer systems. So just wanted to pause here for a moment and see if there's other comments, questions here. Because now we're starting to get to stuff that students really have a problem with.
Sounds good, Ralph. I'm good.
Okay. All right. Good. Okay. So the okay. Let's see. Here we are. Okay. BCD arithmetic is another thing that that students. This is a tricky one. It's widely done. So that the problem here is trying to emphasize to them that the binary coded digits are 0 through 9. Okay. So if you add some things up, like take this number 644 plus 275 BCD, 5 plus the 4 gives you 9, but that 4 plus the 7 is going to give you 11. You can't represent 11 in a single BCD digit. I try to tell them, just think of it like a 7-segment display. I can't write 11, so I need to convert that to a number, and basically it's 11. I can do the 1, the digit of it, which is what I need to do. So you add 6, because basically if you only go up to 10, then you're going to add 6 to get it over 16 to kick the next bit up. So, and then so basically anytime that it's over 9, 10 or above, they have to do this. And this is, they kind of get this a little bit. Sometimes there's errors and they don't quite know exactly the way to do this. I try to have more examples, but that's an important thing. And it is, they do find it interesting when they do this. I used to have a lab that you actually built one of these things. You actually did the addition, and if it was greater than a certain number, it was pretty cool. You just did with gates. If it was greater than 10, you added 6 into it, and you wrote the number out. It was a nice lab. I haven't done it in a while. Students really kind of got to see what was going on. But like anything else, students really need to work several examples of this to get this down. It's a tricky one, and of course, homework and quizzes and things helps. Okay, so this takes you to basically what is the first CTAG rubric layout, which is really what, when we go through this, we have to look and see what level of proficiency students have in each one of these topics that's covered. So there's, I can't remember how many there are, but 10 or so of any of these objectives. So the one here, number systems, operations, and codes. So typically, as I've said in the past, we're really around this area for what goes on. Rarely have I taught a class and gone into like error detection codes. It's more of an advanced topic. Sometimes I'll talk about binary versus gray code. Not so much error generation, but typically here, I don't cover too many fractional binaries, but definitely all the addition, subtraction, operations, binary, hex, octal, all this kind of stuff. So really, most of the courses digital that I see, both at 4-year and 2-year schools, really kind of come in this area. Definitely everything below this is pretty well done. I have talked about ASCII from time to time. I'll give them an assignment, do the lookup tables, and write your name in ASCII or something like this, and students think that's pretty interesting. Done that a few times. It's not something that I would do every time. It's just however much time you have in a course. So this is kind of the first rubric. The next topic we start, I don't think we need this right now. Unless you guys have any comments, I'm just going to move on.
Nothing here.
Okay, all right. So, so next thing we'll talk about really is building the truth table. Okay, so once I kind of get them all, get an idea of what the binary numbers are, the fact that you've got inputs from each wire, and they can have, each one can have 2 binary values, and that the outputs themselves are binary numbers. Then we start talking about building up the truth table. And so I basically tell them that what we have here, is that for these 4 inputs, the output needs to be specified for every possible combinations of those inputs. And then I say, well, how many combinations is that? Well, this is a binary system, so if I've got input lines, there's 2 to the n possible combinations. So for 4 input variables, we have 16 combinations. All right. And so the key point, of course, I try to be sure they understand is they have to start on 0. And they're all 0, and they go up to where they're all 1, which is binary numbers 0 and 15. This is why I try to continually emphasize them on knowing those numbers between 0 and 15. So I show them what basically it looks like. This would be an example. Okay, so I have all the possible combinations of A, B, C, D on the left. And I found out one thing I didn't know was even an issue. Students will write these in a random order, which kind of stunned me. I've seen them do it a couple times. They'll go 0, 0, 0, 0, and they'll like 0, 1, 0, 0, and they try to actually kind of remember it. I'm like, guys, there's a pattern here. It's 0 through 15. Just write them out. And then I tell them, and they're like, well, you could, and they make a good point. I had one student's like, well, actually, it doesn't matter. You can make them any way. I'm like, yeah, that's true. You could, but later on, we're going to be doing K-maps, Carnot maps, and it has to be in a specific order, so-called canonical order. So I say, just make life easier for everybody to do it this way. And I tell them when they're filling out their maps, if you look under A, it's 8 zeros and 8 ones, and B is 4 zeros, 4 ones, 4 zeros, 4 ones. Notice there's patterns to this. It's very, very easy to work out. So this is basically an example of some functions. I just gave them some random values that you could have F, G, and H that have values. These are completely different functions, but they all depend on completely what. But it's all mapped out completely for all the inputs that you have. And so I try to emphasize to the students that ABCD doesn't necessarily represent a number per se. It could, but it doesn't mean that it does. It represents signals, but if you've got 4 signals, you've got 15 combinations, and that's just helpful. So one thing, of course, you have to do is you do a number of exercises doing this. Now, here's the sequence that I like to tell them. This is pretty much what the whole course is about, and that is that you specify some problem. This is given in a lab or giving a word problem, but usually it's some kind of word problem. If you want to build, we have a lab where they have sensors in a chemical tank. They have to monitor pH, and they have to monitor water level. And matter of fact, we have one of our instructors, Randy Adams, who actually, this is a realistic example because he's the one who he's designed all of the sensors for the fish tanks up at Jungle Gyms, and he talks. It's very complicated. You also got salinity and pH and you got a bunch of things you have to keep and make sure all your fish stay alive. And so we have a lab where the students have to lay this out. So you get a problem specified, then you have to develop the truth table. That's almost directly what it is. So for every possible combinations from all these sensors, this light, this alarm, this light, something goes off based on those inputs. And so they have to map that out. Then they write out the function from the truth table. Often the function is too complicated, so they have to Boolean reduce it. We'll talk about that probably next time. By far, Boolean reduction is the worst part of the class. Students always have a difficulty with it, and it always causes problems. Then you build the circuit, and once you build the circuit, you test it. And then I should put a feedback arrow going back. One, when you test it, do you get this truth table that you have here, or do the circuit set doesn't work, so you got to go back and rebuild it? There's kind of a loop here that I probably should have put in. All right. So once they kind of have the kind of idea of the way this works, and I'm a big fan of constantly giving the students the bigger picture. It's like, okay, we just studied this, and this is why we just studied this. So now we're moving on and doing this, whatever that is. I guess there's the classic tell them what you're going to tell them, and tell them what you told them kind of approach. That's pretty appropriate. So I always try to give them a sense of how this all fits together. So this is the key sequence, and so then I tell them that we're going to, before you can actually fill out the truth tables, we have to study the logic gates. Okay, you have to know exactly what's going on because you have to make sense of what of the expressions that you're writing down from the truth table. So you have to have the logic gates. Students usually enjoy the gates because they look kind of neat. They're kind of fun to draw in general. I tell them there's 7 basic logic gates, which they need to know them. They need them. This is one of the things I specify that they need to actually know. And they need to know all the gates by heart. Okay, and so there's a couple of things that I've learned that is important to emphasize. For instance, so you have your AND, your OR, and your inverter here. Basically, I tell them, we go through them. Okay, the AND gate is only going to be, the output is only going to be high if they're both 1. And I tell them that basically we're focused on positive logic. We're only looking at the output, the situation where the output is 1. That's what we care about for the most part. So I say this is where X and Y equal, they both have to be 1. But I tell them also that there's something that's even more important. This will come up later, and I'll probably have some slides on this. That's that this output will be 0 if any of these inputs is 0. That's an extremely important concept in digital electronics because that goes to what's known as an enable. So you can block off large parts of circuitry by having a gate, an AND gate, that has an enable line going in, and all it does is send in a 0, and then everything is shut off. Cuts out everything. So yeah, if you look at the truth table here, if X or Y are 0, the output's 0. They have to both be 1. And it doesn't matter. And I tell them it doesn't matter if there's. And this is an important aspect that you see in Boolean algebra. You could have 15 variables in there, X, Y, Z, P, D, Q, whatever. If one of those guys is 0, that gate is 0. It wipes out the whole thing. And that's a very powerful concept that they need to know, and it's very important in digital design. concept of enabling and using AND gates in that way. Likewise, I tell them the OR gate. If the input's 1, the output's 1. The only condition that you can have with that's not going to happen is if they're both 0. And then the inverter is just an inverter. There's no problem with that. Then we go through the other gates. Talk about the NAND and the NOR. They frequently have a hard time understanding NAND and NOR, but I tell them it's just you just separate out the dot. The dot is what does the inverting. It's just an AND gate, and then you just invert the output. So if you look at it, this is just not AND. That's all it is. It's just the inverse of the AND function. The NOR is just the inverse of the NOR function, of the OR function. So I tell them and I also I'll tell them initially. I'll tell them these are the two most important gates that you have in digital electronics. And later on, I go on to tell them about the fact that you can make everything out of these guys. Then we talk about the XOR and XNOR. Okay, and the XOR basically is this. It's like the OR, except only one of them can be 1, and the XNOR is just the opposite. I also like to specify there's a lot of things going on. The XNOR is commonly used to indicate where you have two signals that have the same value. So if they're both 0, it's a 1, or if they're both 1, it's a 1. So this is used in comparator circuits. So I try to tell them a little bits and pieces here and there about what each one's used for. But I do tell them you need to know these little 2-variable truth tables for every single gate. You need to know them very well. So if I tell them, okay, what's NAND? I want to hear them 1110. I mean, that's what I want to hear them say. And because that really, when they're building more complicated circuits, then they can check those things. Because one of the main emphasis that we have, EET versus EE, is troubleshooting circuits. So one of the things is they have a fairly complicated circuit. We really try to drive home in the lab that they need to look at intermediate points in the circuit. So if they've got two signals coming out of an AND gate, they need to know what an AND gate does, and they can check for that. And so we really kind of drive that. For basic gates, students do have a couple of issues. All right. One, it does take a long time before students will stop saying A times B and A plus B. Okay, and I tell them, okay, this is Boolean algebra. And we'll, of course, go into this next time, but there's no addition being done here. It's A or B. You'll find that 1 or 1 is just 1 versus 1 plus 1 is 2, and we're not doing that. We don't go to 2. Okay. So it takes a while for them to, and I try to correct them as much as possible, even when they ask questions. Okay, we have A times B. I'm like, no, it's just AB. It's just A and B. Students, I alluded to this earlier, where students need to look at an expression like F equals A, B, or C, and they need to back out from that. They need to know that what this really is. That these are actual wires. This is a wire from input A and a wire from input B going into an AND gate. The output of that goes into an OR gate with C, and that goes out, and that's F. So they need to actually kind of understand what that means physically. Students have an understanding why, like you have something like A prime BC. The only time A prime BC, because what is A prime BC? It's A being inverted and put into an AND gate with B and C. So the only thing that an AND gate, the only thing that can give me a 1 is if A is a 0, B is a 1, and C is a 1. Students have a hard time with that, and we have to work on that. I try to really make them understand what that looks like, with the gates and how they actually see that. I try to, I remember I used to teach classes in electricity and magnetism, junior level electricity and magnetism course. And one of the challenges of that course is to have the students, see past the math. That's, vector calculus and a bunch of other stuff. But the idea was, could you actually look past the math and grasp the concepts of what's going on? The math is a tool. It's a language with which you convey these concepts. Here, it's the same thing, A prime BC. That should look to you not like some letters. It should look to you like A has an inverter on it. It's put in an AND gate with B and C. That's where I want them to get to. And of course, they draw a lot of this. Also, I strongly recommend that students use primes after letters instead of the bars over them. For one thing, the bars are not readily available in most fonts. But also, whereas this AB, this NAND version here, AB, with the inverter after is clear, but I get students who will draw a bar and it goes about halfway over the B, and I have no idea what this is. So I tell them to try to use these the representation that just uses the single little marker there. Okay. Another thing that I find is some students do better using some sort of analogy. Some of them have a little better. See, did I drop off? Oh, here they are. I didn't know that happened. Okay, here we are. Some of them are a little better with electrical analogy. Some of them had DC circuits or something before they come to the digital logic course. So I tell them basically, if you're really looking at trying to get current from a battery to a lamp, for instance, I want you to think about what's going on if you had two switches. If you've got one of these switches, closes, the current's going to flow fine and you're done. And this is the situation, like an OR gate, right? If they're in series, then you have to have both of these switches to engage because it's just an open circuit otherwise. This is an AND gate. And then picture that you have a closed switch which only closes when the signal is 0. And when the signal becomes 1, it opens up instead of closes. And this is an inverter. Some students like this kind of analysis because it kind of gives them a more physical feel and ties it back to something that they have some comfort with, which is in parallel and series circuits and switches and things like this. So I usually will give them an example like this. Go to a slightly more complex function. Let's look at what happens here. So I say, okay, I want to get current to the light bulb. What has to happen? Well, right off the bat, they'll say, well, A has to be closed. You have no choice. It has to be closed. Now I've got two paths. So either D has to be closed, which would be fine, or B and C prime have to be closed. So, okay, well, there you go. So the light will turn on under these conditions. It's either A and B and C prime, or A and D. I said, well, there's your logic expression right there. And so this, otherwise, any other condition goes off. You see right off the bat, if A is opened up, regardless of what B, C, and D do, this is a goner. Okay, I said this is the way digital signals work. This is making sense of this specific function. So some students like this. This hits home for a few students and kind of makes sense to them. I think it works well for me. So now what I say is, okay, so now we have the basic ideas of gates. What you need to do now is you need to build the truth table. Okay. So now we have the ideas of digital signals. We understand what the truth table represents. The truth table represents all the combinations of these inputs X, Y, and Z. So that starts to make sense to them. Okay. So let's look at the function X or Y prime Z. Right. Well, okay. So typically, one thing I have to be very careful of is that students will very quickly very quickly try to map out that entire function. They'll try to do it all in their head, and that doesn't work. And I try to tell them, no, you can't do that. What you need to do is you need to put these intermediate states up on the truth table. So for start, for example, let's just take it piece by piece. We'll take the Y prime. So there's Y, so we can write down what Y prime is. Then let's look at Y prime and Z. Okay, let's just use that. Okay, so then we'll Y prime Z. And then, okay, let's look at the full expression. So now all we have to do is look at two columns. I've got X, or Y prime Z. If any of these ones is 1, if any of these are 1, then the output's 1. And so this is not only something that I have them do for fairly complicated circuits in the classroom, or in homework or whatever. I have them do this in the lab. Okay, so the lab is very important in that respect because they have to learn how to test. Here the classic example is this. This happens quite a bit. I have a student who's got a somewhat complicated circuit, and they call me over. They're like, it doesn't work. My somewhat snarky answer to that is, okay, now what are you going to do about it? Okay, you called me over, and I agree. Yes, your circuit does not work. We have confirmed this. What's your plan? Because if they're for EET degrees, this is about troubleshooting and fixing things. So you have to develop the skills for knowing how to pinpoint problems and an approach to doing this. Okay. A lot of times students will have we have trainers and maybe the power supply goes out and they have to figure out what to do. I don't let them drown. I don't tell them you can't figure it out and you're done. I want them to struggle for some time, a little bit. And so what I tell them is, okay, you've got a complicated circuit. It doesn't work. That means somewhere in this circuit it fell apart. So you need to go back and you need to check. You need to check here. You need to check here. You got to figure out exactly where it fell apart. And what do you expect? And sometimes you have to go through the entire truth table for each one of those. You look at all the signals for each one of those things. It's exactly the same thing you do if you were to use, a digital analyzer. You would just put traces at various parts of the circuit. You would take a look at it. I have them map these intermediate states. Also, what it lets me do is when I do this on a test or a quiz, is it lets me see problems that they have. Like y prime z, for instance. If they're not doing that right, then I know they're missing that concept. They're not seeing that as an inverter and an AND gate. And I'll write on the exam, okay, you're missing the concept here. I try to tell them, go back, look at some of the notes, and come see me if you have problems, things like this. So it helps me, versus if they just write down the function, they just have it wrong. I don't know what part of it that what concept they've missed. That's very important to me. So that helps out. So especially if you get a problem that looks something like this. Okay, this is an example that's directly off of a quiz. So it's too you can't just throw F up there. I mean, it's got NORs and NANDs, it's got inverters, ANDs, and ORs. I mean, everything except an XOR and XNOR I threw into this. And it was done intentionally to do so. This is probably not a very nice function at all. But one of the things that I say is, okay, you have these intermediate states, X, Y, and Z. Well, why don't you write those down? And so the students, I tell them, I walk them through this. I say, okay, what is the function Y in terms of A, B, C, and D? What's the function X? What's the function Z? So once they write those down, I say, okay, we'll put on the table, write down what X is. And so they'll fill out the truth table for X, and then they do it for Y and Z. And they say, well, F is nothing but X or Y or Z. I mean, that's it. So then once they have these three columns filled out, then it's just, the F is very simple. It's just this one or this one or this one. So that works out very well. It's slow going, and and typically a problem like this, what you would end up doing is I would have them do the chart, and then there would be 4 or 5 more steps. Then they would take it and they would, okay, I want you to Boolean reduce it, or I want you to do it with a K-map later on, and then maybe redraw its simplified version and with NAND gates or NOR gates or something like this. But this is a very common type of thing. What I do find here, one of the keys of teaching this course is just really trying to figure out where the students are having their problems. When you see like a student for right after he writes this AND gate, you'll see a student that will write down something like B or C. I'm like, wow, okay. Well, the first thing is it's not an OR gate, and 2, they didn't see that it's D coming up, and they see. So they're not following the wires in the schematic very well. And I'll see that a lot. This one, for instance, they may not get that this is a NAND gate, or they'll write C or D, all prime, like it's a NOR gate. And okay, well then I'll tell them you need to go back and you need to study your gates. Makes it different if they completely mess up the function. It makes it a little more difficult to grade because then I have to go through and see if they actually. There's a couple of different skills that are present here. One, can they read the circuit correctly? And even if they write down the wrong function, can they still fill this out correctly? Because they might be able to do the truth table fine. But they just didn't read the circuit right. So you have to kind of check all these things. So that's one of the things. I like to build problems where at least it's illustrative enough to where I can determine where they went wrong. I can pinpoint as much as I can because it's very difficult to get students to come to office hours. The students that do tend to come to office hours are the ones that are doing well and typically don't need to come to office hours. But the ones having real problems, they tend to not show up. So I have to be able to give them feedback somehow, and so that's the way this goes. So this is the second rubric layout having to do with logic gates. Okay. Here you can actually the logic gates portion of it is so critical. the skills really come up about here. In class, I have them go through. I measure the voltage levels. I'm gonna open up another one of the documents in a second here, and I want to go through a couple of things that are done in lab for the last part of this. Because this is for the material here. I'm stopping after this slide for this portion of it. Basically, they have to construct and analyze these logic gates with more than 2 inputs. That's fine. You can look at that. Anytime we have a 4-input word A, B, C, D, whatever it is. Though I tell them that the real situation is that almost all of the TTL gates are 2 inputs. So when I have them do designs, they're all 2-input gates. I make sure they do that. Go through measuring the voltage logic levels. I actually, and I'll show this in just a minute, they actually do go through and measure what is a 1 and what is a 0. And everybody's is different. We have these trainers that they use that they have to purchase, and they go through and they measure. One person's got 4.5, one's got 5, one's got 3.9. Those are all 1. That's fine, but it just shows them that there's some variability there as well.
So when you do that, Ralph, do you do just like a VOM, an analog one, or digital meter, an oscilloscope, or?
Actually, it's we've actually done both. There's a couple classes we have done both the analog and the digital meter. We try to emphasize them to use both of those. Yeah. Actually. Okay. The reason being, and Ray Ellington drove this home for me. And he says that one of the things with using the older analog is that with the needle going up and down, you can really see trends. It's just like an analog watch versus a digital watch. I mean, I like analog watches because I look down, it kind of shows me how much time I have. I have that much, I have this much space, right? Yeah. And it gives me a sense. And the same thing as you're seeing in a digital may give you a more precise answer. But if a signal if you're looking at a sine wave or something like that, and it's rising and falling, you're going to pick that up on an analog meter much better. Typically for this though, the digital, they'll just use the DVM usually. Right. To measure that and pick it up. Yeah. And I try to. Yeah. Go ahead.
Well, that's right. I was gonna segue into another element of the way, like when you're teaching. I mean, your slides are excellent. I mean, they're so crisp and so clean. I mean, I'm curious, number one, what you use to draw your circuits, and then do you use PowerPoint slides when you teach class, or do you normally draw circuits on the board, or what's your MO as far as that goes?
I usually don't use PowerPoint at all. I will only use PowerPoint slides if I need to analyze a circuit which is really complicated. Yeah. And I don't want to spend the time to draw it. Usually I'll draw the circuits. As far as these, this was I don't have access to this software anymore. Which is a shame. This is very nice software. This was for a Mac. And I wish I could remember the package. It was called OmniGraffle, OmniGraffle, and what it allowed you to do was to you could design your own gates. So I could do things like, it's also really good. I could use like I could design multiplexers and flip flops and everything. It had it was. I think it was mostly for doing like. If you're doing like flow charts, flow chart diagrams and things like that.
Right, yeah.
Right, but it had the basic logic gates, and then you could go through and you could modify the gates and do a couple. Like sometimes I'll put inverter dots on the inputs, Okay. And it would let you go through and generate new gates and build it up. The problem was it was only for a Mac, and when I was at OU, I used a Mac for all 8 years I was there. And then I came here. I don't think it's a package available for the PC. Mm-hmm. But it was brilliant. Usually, what I'll do now, though, and I'll probably show some pictures of it later, is I'll use multisim because that's what the students do their circuit simulations on. But I didn't think multisim it's great. It's great for the simulation and everything that's involved. But it doesn't draw really nice pictures like this. Yeah, but I always thought this was really nice. This was something else.
They're nice. Yeah, I mean those are like that. That one, any of those are.
Yeah, they're pretty good. This one was really good, and it was very easy to use. I mean, it didn't have any kind of a routing technique or anything. It wasn't. You had to actually hand draw all of this. and sometimes it was kind of squirrely. That's why you end up getting like crazy things like this. It wouldn't just do something normal, but that's okay. It looked really good, and the main thing I wanted it was to be, you know, it's like I tell the students, it's really unfortunate that the OR gate and the AND gate are very similar.
Yeah, they are. Yeah, if you don't draw them right,
if you don't draw them right, you can't tell the difference. So that's why when I give them a test, I want to be sure to try to use the best thing that I can. Basically, we up here for the rubric here, we're really up here as far as being able to meet all those things. Any other comments with this before I want to open up another file and talk a little bit about a couple of lab things for this section.
So, Ted, are you on there?
Yeah, I'm on here.
Yeah,
I use multi-sim too, and I will either use a green shot to capture just a part of the screen that I want, or I've had luck with being able to actually copy the circuit right into documents.
Okay.
Because I do a lot of PowerPoint and pull a lot of my circuits right off of multi-sim.
Oh yeah. Multisim has been pretty good because you can really cut and paste things. As a matter of fact, you can cut and paste that directly into a Word document. It's great.
Right.
Yeah, and actually, even more surprising I found is that once you cut and paste from Multisim, you can actually edit it in Word. I didn't even know you could do that, but it's amazing. You click on it, you can edit it.
Yeah, and I like using multisim because my students use it to design their circuits.
Right.
So they're more familiar with the symbology and stuff, and it doesn't throw them by seeing something that's even a little bit different.
Yeah, that's true, and it works out well. The only thing you have to do is sometimes you have to turn off all that it's trying to label every single gate.
Yeah.
And stuff like that. So you kind of have to throw that stuff out. But yeah, that's good. It's I try to tell the students. I have a couple of students that actually will even do homework with it. That kind of stuns me. They put that much time into it, but I've seen that happen a few times. When I was an undergraduate, we had a little template. You just drew it. A little thing.
I still have mine. Yeah.
Oh, you do?
I still have mine too.
Mine's long gone. But
I have to admit, I still have my slide rules too.
Oh well, hey, that's a keeper. I mean, that's.
Hey, you got to keep that thing though.
I missed the slide rule era by a hair, so I didn't get one.
You didn't miss much.
Yeah. Well, I still would probably. I'll be one of those people to try to see if I can find one at an antique store or something. It'll be great. But
sure.
I still have my HP that I bought in 1985, and this thing's still going strong. So I'm good.
Yeah.
Okay, so let me go over to let me see if I get out of this, am I still sharing? Let me see. Okay, that's good. So I wanted to open up. Okay, that's good. Okay. All right, I wanted to open this up. So a couple of things. So this document here, which is okay. So this is where some of this information is. It's just basic ideas for I always think it's a good idea to give a little bit of extra, problems and tutorials or whatever's there. Certainly, I just want to provide a lot of that information for whoever's going to be teaching the course. I mean, most people who have taught the course many times usually have their own kind of packet of stuff, but it never hurts to have new problems coming in, and you kind of give the same things over and over. So it's always a nice thing. But for the so basically here, for instance, of course, this is the base of the idea here. I do really want to emphasize that there are 16 different true variable truth tables that students have. I want to be sure they know all of them, not just the gates, but even things that are kind of simple like this one here, which would be x prime y. I really want students just to know every one of those possible two variable gate truth tables. So, like for instance, so this is like for objective 2, this is a lab exercise that we would do. This is the first thing we do, by the way. The first lab exercise that we do here at Cincy State is getting to know the equipment. So we show them the DVM, we show them the OVM, we show them the OVA actually. We show them multisim. So I'll draw up a simple circuit, even though they don't really understand what the circuit is at that point. I show them the basics of how to do it, where the components are, how to find them, and make sure they can do some simple circuits. They'll just do some A, B, or C kind of thing, and then put a light bulb on it, and it'll blink. That kind of stuff. That's basically what the first lab is all about, just getting them an idea about how that works. Also, also, as very important as I find out over and over and over again, is teaching students how to properly use the breadboard. That's another thing. And I find students, even 3 courses, 4 courses into the curriculum, they will still wire stuff up incorrectly in a breadboard, and it's amazing. I have a fantastic Ray Ellington, who I know that you know, Rob, but he's an adjunct who's been teaching forever. He's a master tech. He has a document which is spectacular on wiring up circuits, and it goes into so much detail. It's mind-numbing how much detail is in how to do this. Talking about keeping your leads short, keeping about color coordination, so that because inevitably students, it's a rat's nest of wires. They can't see what's going on, and Ray will go to the point of even going and ripping all the wires out of a student's board and telling him to redo it. I'm not quite that aggressive in the way I do things, but he, the document that he put together is spectacular. I'm gonna ask Ray if he'd be okay if we shared it, because it's really well done and it's in such amazing detail that I think that anybody who's actually really trying to wire up circuits really should have it.
Yeah, that would be handy. I'd love to see that. I mean, it might be really worthwhile sharing if he's willing to do that, like in that section we have on the Tech Prep website.
Yeah, exactly. It's perfect for that. Absolutely. It's a large document. I mean, I can't remember, 10, 15 meg. I mean, it's a very large document because he has a lot of pictures that he puts in of the actual circuit boards and how to do it. But it's really done phenomenally well. And let me ask Ray if he'd be willing to share that, because
sure.
I don't want to. He gave it to me to use in my classes, so I don't want to step on his toes. But let me just clarify that, because it is very well done, and the students do like to have some basic guidelines there. Another thing, actually, and I don't know if you see these in the classes that you teach, but I have students that progressively go online and watch more and more YouTube videos about how things are done. They'll look up a YouTube video on like Boolean reduction, or they'll look up a YouTube video on truth tables, things like this.
Oh, yeah.
In general, I don't have a problem with that, except when it's presented in a much different way than the way I'm doing it in class. And I tell them that I'll say you can do whatever you want. I can't tell you not to. But there is a caveat here, which is it's being presented in a certain way, which is close to the way the book is being presented. If you learn something very different, it may be difficult for you to understand what's going on in class. So I do tell them that, because they really are very much in favor of looking up a YouTube video on practically anything. Okay. So here's like the second lab. The second lab where they actually start going through and doing real testing. And here, of course, the first thing is they have to understand what the pin package is all about. I do usually tell them that the only thing they're going to really hurt themselves with in this class is sticking themselves with one of these pin packages. You'd be hard pressed to do any electrical damage to yourself with 5 volts and a couple milliamps of current. But we do talk about the pin packages and the numbering, and where VCC and ground. Many of them learn quickly that if you flip this thing over, you short the thing out. That you've hooked VCC to ground and vice versa. Many students, and this happens a lot on their trainers, they will at one point or another hook power to ground and blow their power regulator. That happens so often I lost count. So then basically they go through and they wire this up, and they have to do things like they measure the output of a gate. Oh, one thing that is very important, and students have a hard time comprehending the fact, and I don't know if you've seen this, but that there's multiple gates on each one of these chips. They keep thinking this is the OR gate, this chip is one gate. I tell them, no, that's why it's called a quad AND. There's 4 AND gates on this chip. And this is something I have to work with them, because inevitably I'll see a student who's got a bazillion chips laid out all over his board. I'm like, what in the world are you building? And he's got one chip per gate. And so that takes a little time to kind of drive that home. I try to reemphasize that with multisim as well, because multisim you can label each gate as coming from a particular unit. It's like 1A, U1A, so it's from the first chip. It's gate A. that kind of thing. So I try to emphasize that as well. So they do go through and basically they'll use the example, for instance, of an OR gate, and then they wire it up. I do have them to note down what the pins are. They have to demo it to me. I have to go through and sign off on everything, make sure they have it down, and then they have to build each one of the circuits on this side. Excuse me. So they have to build. They have to do the truth table, and they have to verify that it's fine. And this is how they learn all the gates. They get a little confused when they do multiple gates like this. They don't realize the output of one is the input for the second one, and there's 2 gates on the chip. But this is what this drives home. Okay, so this really is the kind of first part of that.
So that lab's got to take a while.
They can usually do it. Yeah, sometimes. Yeah, the way the lab works is well, there's 2 things. One, labs are 2 hours, and it can be kind of tight to get that in.
Yeah.
I've just actually changed. We have a big curriculum change coming up in fall of 2016, and this lab is being extended to 3 hours. Okay,
yeah, I was going to say. Otherwise, it might.
Oh, it is. So what ends up happening is that the students will not finish a lab, and then okay, we'll finish it, next week. Now they have their trainers, so in theory they could wire the whole thing up at home and bring it and show me. So, but they usually don't.
Buy their own trainer kits?
They have their own trainer kits. They buy them. Yes.
Oh, okay. Okay, that's cool.
We use it for DC, AC, Dig 1, and Dig 2. For 4
yeah, I
courses,
think we do that too. That's good. I like that.
Yeah, they're not too much different from the old Heath kits. I mean, they're very similar. It's just it's got a couple power supplies and the breadboard, lamps, and the usual stuff.
Yeah.
And they work out well. So I have to check off all these things. And sometimes, so if they lag behind, it goes to the next lab, and there's a problem where they can just constantly lag behind. It just kind of snowballs after a while. So
you have 2 students per lab station, or 3, or what do you?
No, they're all independent.
Oh, really? So this is? Yeah. Oh, wow.
Yeah, they're all independent.
Well, just your sign-off's got to take some time.
It does. Yeah, it does. You run around, and I'll even have students bring me the kits like during office hours to sign off on stuff, and I even like right after the lecture they'll be like, hey, could you check these out real quick? Mm-hmm. Oh yeah, sure. But that's fine. That's okay. Because it is a little tight. What's really tight is the class that's taught at night, where it's just one. It's like 6 to 10:30, and you have the lecture plus the lab. That's really tight. But anyway, so yeah, this is the basic idea. Kind of moving. I guess this goes to objective 3, which is coming up. But then we just build up to more complicated circuits. That's all. Basically, once they wire up here, then they wire up another one, and then we start, basically, building on from that. So really, this first lab is really critical, and they really have to, really understand how that works, and basically understanding there's multiple gates, all these types of things.
So. Did you guys develop these labs, Ralph, or are these out of some kind of a digital reference lab book, or? No,
we actually developed these.
Cool.
This was laid out by a instructor before my time. Okay, but someone you probably know. What's his name? Tall guy.
The tall guy. Yeah, I know who you're talking about. I know exactly who you mean. God, his name's escaping me too. I'll think of it before we end here.
He was here forever, but anyway, yeah. But the thing about it is, and this is a lot of the labs. I'm going to be changing a lot of these labs, and because they're still a little bit more design focused than troubleshooting, and so what ends up really needing to happen here in something like this lab is I kind of almost need to give them an unknown chip. Here, wire this up and tell me what this is. Or something like that. Something like, or here's a truth table, here's a circuit, these two don't match, fix it.
Yeah.
This circuit needs to look like this truth table. So what's wrong with it? They're using the wrong gate. Maybe one of the gates is blown out. Now we've done that in the past. We actually have had built these little circuits that we gave students that didn't work, and the students had to figure out what was going on. And it's a good idea. It really needs that more of that needs to be done, because what I'm finding is that I'm getting students in later courses, and they just don't have the troubleshooting skills. And that's pretty much almost what this degree is about. They really, it's like I said before, you don't go in the workforce, and they don't hand you circuits that work. Your job is to figure out why they don't. So I think that needs to be emphasized early on. So when you see something like one of these multiple connections, like these dual ands or dual ors, students will mess them up. And I try to tell them, okay, just take a look and see what you're doing. And that's why I have them analyze all those intermediate states and everything when it gets more complicated. So I just wanted to show that basically for those first couple of objectives, this is what we do, and you can kind of tell, you kind of have to really check the students and see who's kind of getting it and who's not. I'm always stunned at students that are phenomenally proficient in lecture, and then they get to the lab and they can't put anything together. One problem I also see is that they'll have switches. The switches are 0 and 5 volts, whether you flip them. And I'll see students will be using some switches for zeros and some switches for ones, or something crazy like this. They don't get the concept that the switch goes between zeros and ones. And I've had students do that, and a number of other things that you don't expect. So it's very good. You have to kind of really walk through them early on so they get these concepts down. The breadboard, for some reason, I'm not exactly sure why that is. They kind of hit or miss with that. I try to drive home the idea that you really want to have a power bus on the top and a ground bus on the bottom, and pull all power and ground from that. That's explained in Ray's video, actually. Not Ray, but his document, which is really well done. But this is the only one I want to show. So kind of what I'm going to do for some of these other for the other courses in this, the next topic that I'm going to pick up on Thursday is going to be Boolean algebra. That's a good portion of it, and K-maps. Basically going through all that reduction stuff, showing a lot of examples and problems students have with it, and then basically doing truth tables and everything with that. And then I'll just march through that way. And I want to talk about the labs we have in support of each one of those, and we'll do it that way. But for right now, I think this is about it for today.
Good. So Mike Carroll is the guy, right? The guy
no,
not Mike.
Mike. Yeah, no, Mike. Mike did some instructions. He's not the one I'm thinking of. It's
That's right.
Oh, I can't remember his name. I never met him actually. He used to do the senior design course here with Linda. Bob. His name's Bob.
Okay. All right. Yeah.
And I forget.
I know who it is. Yeah. Hey, so Ted, are you a Project Lead the Way program, or?
Yeah, I do Project Lead the Way.
Now, do you guys? What about labs in the Project Lead the Way? Do they come in a structured kind of format, or do you have to create your own, or how's that work?
They come in a structured format, but you have the freedom to adjust them and create your own if you want, as long as you're meeting the goals.
Yeah.
For the students, but they're pretty structured. So you start off with a lot of breadboarding at first with some simple logic things. Like right now, my guys are doing a voting machine where they have a president, vice president, treasurer, and secretary voting for their inputs.
Right.
And then they have to just have an output as to whether it passes or not.
Right.
But that's their very first one, and we pretty much just let them explore a little bit. We really have not gotten into K-maps, and I'm just starting to develop the truth tables with them. So it's more of here's some AND gates, play with them.
Right.
And then we try to structure them a little bit more as we get into other projects during the year.
I think there's something to be said about digital, like the number systems, the concept behind it, that I think enhances a person's understanding in other mathematical things. I don't know. I know whenever I take students through sort of the development of a number system, how do you get to the binary, how the binary codes values and so on, they're intrigued, and it's like, wow, that's pretty cool. I never thought of number systems the way we're now looking at number systems, you know, and then, of course, if you segue over to code, like you just did with the BCD,
Right.
it becomes a pretty powerful.
It does. It does. And, you know, it's, you know, basically anytime you step back and you say, okay, well, everything that you know of from this point is only one option, you know, of this whole thing, then the students do get kind of surprised by that.
Yeah.
Yeah, when you say, okay, you could do this in base 5 if you wanted to. You could do it in
Yeah.
base, you know, whatever.
Yeah.
Yeah, I've done that in the past. I've done some things. I've given them, you know, just convert to base 5 just for kicks or something like that, just so they know that there's anything particularly special about base 10. It's just, you know, it's what we've chosen. So.
Yeah. Yeah. Exactly. I got to tell you guys, I don't teach digital. I have before, but I just love the subject. But part of my CNC programming stuff, we look at the bits on a punch tape, and I talk about the ASCII code, and so I go a little bit into this, and not the gates and stuff, but the number systems. But I terminate the 8-bit number with a Wendy's hamburger slogan, and they used to have a slogan that said, "We'll make you a hamburger one of 256 different ways."
Right.
So I always tell them, yeah, you just go out and get, you know, you start with your plain burger with a, you know, and that's like all zeros, and then you get lettuce, mustard, onion, get 8 items. You know what I mean? It's either on or it's off. And I you know, make a joke. You could say I want light mustard, but you're going to get a squirt of mustard. It's all the same. And then a kid brought in a fries box, a French fries box, and lo and behold, they had the slogan on the side of that French fries box. So I scanned that thing in, and I show the students that to email that to you. It's a fun conclusion to a discussion about the combination of bits, and, you know, 8 bits and 256 different combinations and things like that. Actually, I take it on to 10 bits. I say, yeah, you want to know what K is in computer jargon. It's always powers of 10.
Sure.
I said, so your next grill out, instead of having 8 items, you know, get 9. Then you got 512. No, go get 10 items. You know, a couple kinds of cheese or something.
Yeah.
Come in and make your hamburger more than 1,000 different ways. You know, and 1,024 in fact. So.
There you go.
Yeah. And they just. That, so.
It's funny. I'd forgotten about that. That was a while ago.
Yeah, it was. Oh, the Wendy's hamburger thing was a long time ago, but it stuck with me. Well, actually, Ralph, I was probably teaching electrical things at Cincinnati State. You know what I'm saying? I probably was. Yeah. And that they came out with that, and I said, holy crap, that's a perfect application, and I brought it in, and I've used it ever since, but I never had something formal other than people recollecting that now the farther we get away from it, the less they remember it. But when that student brought that fries box in, I bet you it was only 3 years ago, and I still have that. I'll email it to you guys.
Yeah, dude, actually, that's a great image. I'd like to put that up on a PowerPoint somewhere.
Yeah, because it's fun to do, and of course it kind of then sticks with them a little bit too, you know. So. Yeah,
it was really funny. When I first went to OU in 2005, this was the first course they asked me to teach, and I hadn't taught this. I hadn't even seen this material since 1986. At the time they asked me to do it, and I just found out that I really enjoyed it. I just really enjoyed teaching it, and even as many times I've done it now, I'm always surprised that I see something a little bit new each time. Some student will see something differently that I've never seen before, or there's just new challenges. It's just the way it is, and you know, I think that I'm much more focused on being, or at least I'm better at trying to find the core things that the students have problems with.
Mm-hmm.
Because I have enough data now to where I can actually kind of pull that out and see what common themes that students are having problems with. And but still, one thing I see, and you've probably seen the same, and you know, that's there are students which just take to this like water. I mean, it just makes perfect sense to them. I don't know if they were the kids that built things, or they were chess players, but they just have a naturally inclined logical mind.
Yeah.
And there are some students which just struggle, and they can't. They have a really hard time understanding the Boolean signals and the combinations of things. And I find it the most difficult to deal with those students trying to figure out where they're having a hard time with it. And I've got a great, for instance, when we do Boolean reduction, I'll show it next time. All they do in textbooks is they just give you a bunch of rules and say, okay, go apply them. But I actually developed a whole process for doing this, and it's really helped the students a lot to go through doing it. And and because I just noticed that students didn't have a framework or some sort of blueprint for doing this. And so I just kind of takes a while and kind of see these things. But I still enjoy teaching the class. I try to teach as often as possible. So.
Yeah, it's a great course. Your stuff is really well done, Ralph. This is nice.
Well, there's a lot of data here. Yes, I mean I've got files and files. So I definitely want to convey to anyone who's sitting in the course, listening to the course, that if they're having a hard time finding some sort of examples or some problems that to illuminate some particular idea, send me email, call me up or something, because I can send more practice problems than you can think of, I've got a textbook worth of stuff that I've created, and so everybody's welcome to it. I'm not going to write a textbook. That's too complicated. I don't want to deal with it.
Yeah. Well, you've been great. This is excellent. Ted, thank you very much for being here. We appreciate your commitment. Terry, I'm sure we'll reach out to the other people who've signed up because we had a really good group with the DC, and we thought every one of them would certainly follow along with us. They expressed interest in us.
Okay.
And we'll figure out what's going on. So.
Yep.
Thanks a lot, guys.